Welcome to our geography discussion on synoptic weather maps. All right. When you're talking of synoptic weather maps, this is basically a geographical concept which is applicable in the FET phase, starting from grade 10, grade 11, and ultimately grade 12. So what I'm going to present here, I'm mainly going to focus on the basics of synoptic weather maps, the basic understanding of synoptic weather maps, primarily based on grade 10 content, so that maybe you can grasp the basic concepts. If you're in grade 12, it means the content will be, for the synoptic map, will be linked to the weather phenomenon typical of grade 12 content. Like you'll be analyzing synoptic maps involving the weather phenomenon like the tropical cyclones, the mid-latitude cyclones, the traveling disturbances associated with subtropical cyclones, anticyclones, and all those aspects in grade 12. But for the sake of the initial discussion here that we want to do with on the synoptic maps, my focus here is basically on the basis of reading and interpreting synoptic weather maps. Right. So what I have here is a symbol of a synoptic weather map, which basically has got the basics, and I will use those basics to ultimately clarify, and also at the end, we'll try to relate some questions posed to the given synoptic map, which is after this discussion. Right. Let's start by analyzing the synoptic weather map. Right. What we call a synoptic map, by the term synoptic. Basically, when we're talking of a synoptic map, we are looking at a map that gives us a summary of the weather. It gives us a summary of the weather conditions at a given place, at some given time period. So we are saying a synoptic map summarizes the weather of a given place. And it summarizes in terms of the weather elements. It gives us a summary of the weather elements. Right, which weather elements are we talking about here? We're going to look at specific weather elements and how they are summarized on the synoptic map. As an example, when we're looking at some weather elements, we're looking at aspects like precipitation. What kind of precipitation is likely to be received or has been received at a given space? Precipitation, we are looking at all kinds of moisture coming from the atmosphere, which come in the form of hail, in the form of rain, in the form of snow, in the form of drizzle, in the form of all those forms of precipitation of moisture are reaching the Earth's surface from the atmosphere. That is with precipitation. So the synoptic map can also give us a summary of the precipitation that will be received or that is likely to be received at a given geographical space. Then it also gives us a summary of a weather element like cloud cover. It summarizes also on cloud cover. And on cloud cover here, it gives us a summary of the percentage or the fraction of the atmosphere which is covered by the clouds. So our cloud cover, basically, when you're talking of the measurement of the amount of atmosphere which has been covered or which is covered by the clouds, we use the concept of octas, or which we call the eighths, which is a fraction over 8. Right, so we are referring here to a fraction over 8 as our cloud cover. We are saying our full sky is 8 out of 8. So we try to determine the percentage out of the fraction out of 8 which is covered by the clouds. We are going to look at it when we go back to the synoptic map and see how it is portrayed, the different amount of cloud cover, how it is shown on the synoptic weather map. Then we can also look at other weather elements. We've talked of precipitation, we've talked of cloud cover. We also look at the temperature as a weather element. Temperature, remember we have two measurement of temperature in 2 dimensions. We have what we call the minimum temperature and what we call the maximum temperature. And also, when I'm looking at it in another geographical perspective, this is the dew point temperature. So those two, they refer to one and the same thing. The minimum temperature is also called the dew point temperature. Then the maximum is also called the air temperature. So it's also analyzed on the synoptic map. We also have an indication of temperature for a given geographical space in the form of the minimum temperature, which is the lowest expected on a particular day, and also the maximum, which is the highest, which is expected on that particular same day. Right, that is element number 3. Then we can also talk of other weather elements, which can also be summarized on the synoptic map, on the synoptic weather map. There are also other weather elements which can be summarized. Like if we come here, you see that it's talking about precipitation, talking about cloud cover. It's also talking about wind direction. It's also another weather element which is also summarized on the synoptic map. We have wind direction. It's also summarized there. And also maybe what we need to highlight here geographically, when we're talking of wind direction, we are saying in geography, we name winds according to their direction of origin. Direction of origin. For example, winds which are coming from the east. From the east, they are named easterlies. For the sake that they come from the east, here, winds coming from the east, geographically we name them as the easterlies. We name winds according to their direction of origin, where they come from. That is how we name them. So winds coming from the east, they are called easterlies. And also, if we talk of winds coming from the west, we also call them westerlies. That is how we name our winds geographically. So there is a way of indicating wind direction on the synoptic map. When I'm summarizing the weather elements, I'm going to show and actually give some details on how the wind direction is also portrayed on the synoptic weather map. Right, we move on to other aspects like wind speed, as we had noted there. Right. Our wind speed is also another weather element which is summarized on the synoptic map. Right. Our wind speed here is measured in units that we call the knots. Right. So we're going to look at how the knots are presented on the synoptic map as a summary. But basically, we are saying the wind speed is also summarized on the synoptic map and is summarized in the term of units of measurement, which are the knots. Right. And also, we can have another weather element which is also summarized like the atmospheric pressure or the air pressure. Our atmospheric pressure is also summarized on the synoptic map. And this one here, the units of measurement, which are used, the standard units of measurement we used on the synoptic map, we use the units called the hectopascals, which is HPA, the hectopascals. Those are the units of pressure which are used on the synoptic maps. The HPA unit or the hectopascals, it's a unit which is used when you're summarizing atmospheric pressure on the synoptic maps. Right, that is just a highlight of what is happening or what happens with the synoptic weather map. Right, we are going back to our synoptic map and try to analyze and see to it how those two, different weather elements are portrayed on the synoptic weather map. Right, we come here, that is our synoptic map. And as we look at our synoptic map, we can actually see that we have some concepts there which are indicated. We have summer and winter conditions, like what is indicated here, summer and winter conditions, like we can see there. It's written summer and winter conditions. Identified by looking at temperature of places on the map and the position of the pressure system. Right, when you want to determine on the map whether it's a summer map or a winter map, we identify by looking at the temperature of places on the map, as indicated here, and also on the position of the pressure system. I'm also going to explain on the pressure systems, but before we look at the differences in synoptic maps for winter and for summer, let me just start by looking at the basics of the synoptic weather map so that we'll be able to figure it out. Right, then we have weather symbols. Or weather symbols, they represent weather conditions at a particular place. Like these symbols that we are seeing here, this is a specific geographical symbol. This is a symbol. They are meant to represent some different weather elements, and they tend to be used internationally as an international benchmark of the indication of the different weather elements as a summary of the synoptic weather map. Right, then we have the standard symbols. These are used to represent information about each weather element. The standard symbols which we use there. Right. Then let's go to the weather symbols which are used on the synoptic map. Right. What you should always keep in mind is you should know these weather symbols as how they are drawn, as they are shown on the synoptic map. We have this one here. You can see the symbol, which is just like something like that. It's like a 9. That is a symbol for drizzle. And we have an inverted triangle. This one that we have here, that's a symbol for rain shower. And then that dot is a symbol for rain. And you see the star there, it represents snow. And then that triangle, which is placed up, is for hail. And if we check that symbol, this is a most common symbol, right? Drawn like this, and then with an arrow. That is a symbol for thunderstorms. When you have typical weather conditions that are likely to produce thunderstorms, that is like during the prevalence of tropical cyclones, we are likely to have thunderstorms. That is typical of the sign of the thunderstorms. Then we have those two lines parallel to each other. That is for misty condition. Then if there are three parallel lines, that is for foggy conditions. Right, so basically, you must try in as much as is possible to remember these symbols as they are drawn, so that when you get a question which requires you to identify the weather element, you are able to figure it out from your mind. Right, and all these symbols here, like what I said earlier on, I've been talking about precipitation. These are different forms of precipitation. They are all symbols of precipitation. And we said precipitation, we are referring to the moisture that reaches the Earth's surface from the atmosphere. So all these ones, they are symbols for representing different kinds of precipitation. Right. Then we move on to other symbols. We have symbols on cloud cover. We have been talking about cloud cover, and we said when we are measuring our cloud cover, when determining our cloud cover, we determine it as a fraction of 8, or what we said, we use the term octas to refer to the amount of cloud of the sky which has got cloud cover. So we want also to go and analyze and see how the different amounts of cloud cover are portrayed or are shown on the synoptic weather maps. Right. We come here. These are the indications of cloud cover. Right. We see here the circle is not shaded, it's just clear, meaning to say there will be a clear sky over that particular space. Clear sky indicating that there is fine weather, there is no cloud cover. It's typical of stable conditions over that particular geographical space. Right. Then we have this circle with just a line in between, like what you are seeing there. There's just one line which is drawn at the center of, through the center of the circle, from the circumference to circumference through the center, like how it is drawn there. That is 1/8. It signifies that there is a unit of 1 out of 8 units which has got a cloud cover. And then we also have that one that you can see there. It's representing basically a quarter of the whole circle. like if you can try to estimate how much of the circle is shaded here, that is typically 2 parts out of the 8. So these 2 out of 8, we can further reduce them to 1 quarter. So it means a quarter of the sky will be covered by clouds. Then we go to other symbols. Again, you can see there is that quarter, and again, the line which continues here. Remember, we said the line represents 1 over 8. Then that means there's 1 over 8 plus 2 over 8. That gives us 3 out of 8. So this one, this continuing line represents 1, and then that one is a quarter. So a quarter plus 1 over 8, that gives us 3 over 8. Right, then we go to the next indication here. That is half of the sky is shaded. You can see the circle is divided into 2, and the other half is shaded, meaning to say it's 4 units out of the 8 units of the sky which are covered by clouds. Then if we move on to the next one, you can see there is this half which is shaded, and on top of that half, there is again a 1 which is crossing by this line here, like what you can see. So it means it's 4 over 8 plus 1 over 8. That gives us 5 over 8. And then we move on with our shading, right? We said this one is a half, and you can see this one is a quarter. So we are saying 2 over 8 plus 4 over 8. That gives us 6 over 8, which is 3/4 of the atmosphere, which is shaded by, which is filled by clouds. Means 3/4 of the sky will be having cloud cover for that instance. Right, then we move on to 7 over 8. It simply leaves out the center or the mid part of the circle unshaded. The other side is fully shaded, so which implies that this is 1, which is clear. And when it's 8 over 8, the whole thing is shaded. The whole circle is fully shaded, meaning to say the whole sky is in cloud cover. Then we move on to sky obscured, which is we put a cross within the circle. That means the sky is obscured. When we're talking of a sky being obscured, we are saying there are more clouds than the sky could contain. Basically, it's 9 over 8 in some other instances. When we talk of the sky being obscured, they represent it sometimes as 9 over 8, meaning to say we have even more cloud cover than what the sky can contain, to the extent that we have even some low-lying clouds which come and be realized as misty or foggy conditions. The sky is overwhelmed, is obscured, right? So basically that is with cloud cover. When we're talking of cloud cover, we are referring to those particular aspects and the different shading, which is used to show the different amount of cloud cover, and also how it is geographically presented on the synoptic weather map. Right, we move on to our wind direction. Right, when we're talking of wind direction here, remember we said we name winds geographically according to their direction of origin, and we basically use our points of the compass to determine our wind direction. So here we are seeing we have our compass, which is showing our compass points. Right, we have the major points, which is north. If you can try to see there, we have our major points of the compass, which is the north and the south. And always remember, on your left, there is west, and your right, there is east. Then in between there, we can also add the other 4 minor points of the compass. Like between north and east, we can have our northeast. And then between east and south, we have our southeast. And between west and south, we have our southwest. And between north and west, we have our northwest. So those are our points of the compass that we can use to refer to wind direction. We have a northeasterly wind, which is coming from northeast, a southeasterly wind coming from southeast, a southwesterly wind coming from southwest, and a northwesterly wind coming from the northwest. Right. So basically, those are our points of the compass that we use to refer to wind direction. We refer to those compass points to actually determine our wind direction on the synoptic map. Right. We move on to the France. The fronts, basically, with grade 10s, you just need to understand the basics of the fronts. And with grade 11, you need to add more detail. And with grade 12s, that is where you have to apply the knowledge of the fronts. When you talk of the mid-latitude cyclones called front and warm front. Right. So basically, we are talking of a front. A front, basically, to simplify it, what we call a front is basically a boundary. That's a front. When talking of a front, we are looking at a boundary. So our boundaries, they differ. Remember, what makes the boundary is the fact that if we have two different air masses, those two air masses basically cannot mix if they are of different properties. Properties, what are we saying? If we have a warm air mass and a cold air mass, their properties in terms of temperature, they are different. One is warm and the other one is cold. When they happen to meet, they cannot mix. So there will be a boundary which will be formed in between them because of their differences in properties. And also in terms of moisture content, one air mass can be dry, while another air mass is warm. That will also result in the formation of a front. Right, or let me summarize it in writing. Right, when you're talking of the fronts, we said basically a front is a boundary between basically two air masses of different characteristics. And amongst the features of the air masses, we said if the air masses are different in terms of temperature. What are we saying there? In terms of temperature, we are saying one can be cold, while the other can be warm. Those two air masses are different in terms of their properties of temperature. They cannot mix, therefore there should be a front which will form in between them. Right, and also we can talk of the differences in air masses in terms of their moisture content. What are we saying here? Air masses can be different in terms of moisture content. One can be moist, while the other one can be dry. These two air masses are different. One is moist, meaning to say it contains moisture, and some is dry, meaning to say it doesn't have any moisture. So those two air masses cannot mix because of the differences in properties of moisture content. And also we can talk of, in terms of stability, an air mass can be stable, while another one is unstable. When we're talking of stability, we are saying if an air mass has got stable conditions, it has a tendency of sinking. An air mass which has got a tendency of sinking creates stable conditions. And if there's unstable conditions, the air mass has got a tendency of uplifting or rising. This is rising and this is sinking. Those two air masses cannot mix because of their differences in stability. One is stable and the other one is unstable. Right. So basically, when we're talking of the fronts, we have basically what we call a cold front, a warm front, and then we can also talk of an occluded front. Right. What we call a cold front in geography, a cold front is basically formed when cold air is advancing towards warm air. So we are saying there's a situation whereby we have cold air on one side, and then we have warm air. So it means if there's this situation, cold air advancing and warm air on this other side, what is going to happen? It will mean that if there's this situation that there is cold air, and let's assume our system is going in that direction, that is going to mean that this warm air here, this is the cold front, the boundary separating the warm and cold and warm air. This is our front or the boundary. These two air masses cannot meet, but this cold air, because of its density, it's heavy. It's more denser, and this one is less dense. On the front there, it means the colder air is going to undercut and the warm air is going to be uplifted because of its density. This one will gradually be forced to rise because it's less dense, while this one is going to occupy the lower parts of the atmosphere because of its density. So when we are indicating a cold front, this situation here on the synoptic maps, we use these triangular inclinations on a line like that. This represents a cold front. So that symbol, a line with some triangles on it, that is a cold front. When cold air is advancing towards a region which is occupied by warm air. That is a cold front specifically. Then we go on to the warm front. The warm front, basically, we are saying it's warm air which is advancing towards cold air. Warm air advancing towards cold air. Like if we have warm air here, this is a warm sector, and we have a boundary that is likely to form. Cold air is there. So our system is moving in that direction. Cold air is trying to push towards warm air is trying to push towards cold air here. What is the result? Warm air, because it's less dense, it cannot effectively push towards this side with cold air. And what is going to happen? The cold air will keep occupying the bottom part of the atmosphere, whilst the warm air will gradually get displaced into the upper atmosphere because it's less dense. So as a result, that is the situation whereby we have a warm front. So a warm front, when we're indicating it geographically, we are saying we use a line and we use some semicircles like that. This is different from the triangles. These ones now are semicircles that we put and we shade them, shaded like that. The semicircles on a straight line. That is how a warm front is indicated on a synoptic map. So whenever you see this, it means there is a warm front. Warm front meaning to say there is warm air which is trying to advance into an area with cold air. Right, then what you call occlusion, there's also an occluded front. Right, when we talk of an occlusion, we are saying this is a situation when warm air has been completely displaced from the ground surface. By cold air. We have a situation we were seeing in the cold front and in the warm front. We were saying there was a situation whereby cold air was undercutting warm air. Undercutting meaning to say because of its density, it tends to occupy the ground surface while it's forcing the warm air, which is less dense, into the upper atmosphere. So at the end, the cold air will effectively displace the warm air into the upper atmosphere, such that the whole ground surface is occupied by cold air, and warm air is only occupying the upper atmosphere. That situation is what we refer to as an occluded situation, or an occluded front, where warm air has been displaced completely from the ground surface and is now only occupying the upper atmosphere, while the whole ground surface is now filled with cold air. So geographically, when we are indicating an occlusion, it's indicated as a combination of both the warm front indication and the cold front indication, like the triangle for a cold front and a semicircle for the warm front. A triangle for the cold front, a semicircle for a warm front, a triangle going like that. So we are seeing we are interchanging our symbols. This is a symbol for cold front. This is a symbol for warm front. This is a symbol for cold, symbol for warm, symbol for cold, along the same line. That is what we call an occlusion or an occluded front. So coming back to our synoptic map, we can see when we're talking of the fronts, that is basically how they are indicated. The cold front with those ones, the warm front with this, and the occluded front with those ones. Right, that is with the fronts. Right, we tend to move on and look at the aspect of wind speed. We want to analyze how wind speed is indicated. We said our wind speed is indicated using the knots. So, indicating on the synoptic map, we tend to find that our knots are indicated at the end of the bar here. We have a circle, then we have a bar, then our wind speed is indicated at the end of the bar here, what we call the feathers of the bar here. Yes. So if it's 1 to 2 knots, there's nothing which is indicated there. At the end, it's just the bar which shows wind direction, and there's nothing. Then if there's 5 knots, you can see that there's half a feather at the end of the bar. And if there are 10 knots, there is 1 full feather at the end. And if there's 15, it means it's 10 plus 5. 10 is indicated by 1 full feather at the end, whilst half of it is indicated by half a feather at the end. So a full plus a half, meaning 10 plus 5 gives us 15. Then when there are 2 full feathers at the end, like what is indicated here, we indicate that is 20 knots. It's 10 plus 10. Then when it's 50, we put that triangular inclination at the end, like what you are seeing there, to indicate that we've reached 50 or more knots. Right. Then we move on to our pressure systems. Right. When we talk of our pressure systems, right, there is a high pressure and a low pressure. Like an H, if we check wherever we find an H, the H is representing a high pressure, and also an L will be representing a low pressure. Right. So let me try to summarize the weather elements like in this weather station here, and try to figure out and explain to you what it means. Right. We come back and try to make a simple illustration of our weather station. Right. I will just use a symbol weather station to analyze what we want to discuss here. Right. If we check our weather station, let's say it is indicated by a circle. Then after that circle, we have a bar which comes from the circle. And at the end, maybe we have this. Right. Let me add another one like that. And then we tend to find that maybe that there are 2 numbers. Maybe it's 10 and maybe it's 32, like this. Right. I want to try to summarize the weather elements there. And maybe we also have another symbol, like maybe there's just a dot there. Right. We want to analyze and see what this weather station, what kind of weather is likely to be for this weather station here, given the summary of what we are given here. Let's say in our circle, it's like this. Right. I will start by this circle here. This circle here that we see is for cloud cover. It's representing the amount of sky which has got clouds. And then these 2 digits that we see here, 10 and 32, they are for temperature. And the direction to which this one is pointing to, this bar here, which comes from our cloud cover indication, this is for wind direction. And we come to the feathers at the end of our bar here. These ones are for wind speed. And then this symbol that we are having here, this is a symbol for precipitation. The different kinds of precipitation can be indicated depending on the precipitation likely to be received on that particular place, given the weather conditions. Right. So what are we saying here? We are saying when you're talking of cloud cover for this weather station here, we can see that it is half of the skies which are having cloud cover. So in terms of our octas, that will be 4 octas, or in terms of our eights, that will be 4/8 of the sky which is covered, which we translate down to 1/2 of the sky being under cloud cover. Then with our wind direction, we are saying where this bar is pointing is where the wind is coming from. And remember, we said geographically, we name winds according to the direction of origin. So this bar is pointing. If we are to determine the wind direction here, we draw our compass in the circle here. This is our north, this is our south, our west to the left, and our east to the right. So if we check, this is northeasterly wind. So our wind there is a northeasterly for that specific station. And then we come to the wind speed at the end of our bar here. We said 1 full feather here for the indication at the end is for 10 knots. So we have 10 plus 10 plus half of 10. It means the wind speed there is 25 knots. Right. Then we go on to our indications of temperature. Remember, when you are asked the question, and the question wants you to determine the maximum temperature or the minimum, the dew point temperature and the air temperature, remember to put the units of measurement. Because here on the synoptic map, they will just put figures without units of measurement. It is now up to you to determine the units of measurement of temperature. We know that our temperature, we measure it in degrees Celsius. So for that effect, we want to have a situation whereby you extract the digits that you have on your synoptic map and put them in the right units of measurement of temperature. So given these two figures, if we have 10 and 32, 10 definitely it means that is the dew point temperature or the minimum temperature for that station. And the bigger number, it represents the maximum temperature or the air temperature for that matter. So if the question is asking for the maximum temperature and minimum temperature or dew point, for this instance, our dew point temperature is 10 degrees Celsius. Our air temperature is 32 degrees Celsius. Give the right units of measurement of our temperature. So basically, that's the summary. And if there's precipitation symbol there, that dot for precipitation, it represents rain. So, which means the kind of precipitation that is likely to be received there is rain. So that is basically how we read and interpret synoptic weather maps, giving a summary of the weather elements on a given weather station. Right, going back to our synoptic map, we want now to try to analyze what is happening on this synoptic map here, relating to all the concepts and ending up relating to our summer and winter conditions. The suggestion given here for us to determine whether a map is a summer map or a winter map, we are told of us checking on the temperatures of places, and also we are told of checking the position of the pressure systems. Right. If we check here on our extreme west part of our map, that is around Walvis Bay, we have a low pressure, which is indicated here. And by the way, these lines that we see on a synoptic map here, these various lines with digits here, I think is also very important for me to illustrate something which is very important. Right. Let me use our writing board to illustrate about those lines. Right. Let's say you are seeing, maybe there's an L and there are some lines like that. Right. And maybe those lines have got some figures. Maybe this is 1008. Right. 1012. And then 1016. And maybe there's another one which is going there. It's 1020. Right. These lines here, we call them the ISO bars. Do not think of contour lines when we're talking of synoptic weather maps. Contour lines are there to indicate height But isobars are there to indicate the pressure. So when you're talking of topographic maps, we talk of contour lines because they are giving us the shape of the landscape. And how can we determine the shape of the landscape? We determine it by its height. How does the height differ from point to point? Through reading the contour lines. But here we are dealing with weather elements. We're not dealing with topography. We are dealing with the weather. So what we have there on those lines are called the isobars. And those isobars are there to show us places of the same atmospheric pressure. They join places with the same pressure. So it means along this line, the pressure is 1020 hectopascals. And then places which are joined by these lines have got a pressure of 1016 hectopascals and 1012 HPA, going like that until we get to the low. Right. This L here, we said it represents a low pressure cell. And if we try to figure out, let's look at the differences between the value of our isobars. The outermost here is 1020, and the one which is following it is 1016. If we try to find the difference here, we tend to find that the difference is 4 hectopascals. If we try to analyze again between these two, it's 1016 less 1012. We tend to find that the difference between the two is again 4 HPA. This is what we call isobar interval. Isobar interval, we are saying, is the difference in pressure between two consecutive isobars. By how much are they differing? 1020 minus 1016, the difference is 4. 1016 minus 1012, the difference is 4. 1012 minus 1008, the difference is 4. That is the interval of the isobars. They maintain the same difference in pressure. As long as we have two isobars next to each other, their difference maintain the same. And that is going to help you to determine, for example, if there is a missing value, and the question is asking you to determine the value of that isobar whose pressure is not indicated. Like for example here, there's 1008 inside the low pressure cell, close to the mid of the low pressure cell. Then there's 1012. Then this one is missing. It's letter A. The question says determine the pressure of isobar A. Then there's 1020. Automatically you can figure out from the sequencing of the isobars. If this is 1008, we are coming from a low, we are going out of the low pressure cell, meaning to say the pressure is increasing outwards. We are moving from the center of a low, the pressure increases outwards. And if you are going inwards, the pressure decreases. So if you are looking at the value of the isobar on the outermost part here, should be higher than the value of the isobar in the mid, which means we are subtracting as we are going towards the center. The moment you determine your interval, you subtract the interval to find the values. Or if you are coming we are coming away from the center of the low, our values are increasing going outwards, meaning to say we are adding up. This is an addition. In this direction, we are adding the interval, and here we are subtracting the interval. We are going to the low, we are subtracting, we are going away from the low, out of the low, we are adding the interval. That is basically what you must do when you get a question which requires you to calculate the missing value of an isobar whose pressure is not indicated. Right. That is basically the idea with isobars. And also you should check, that is the sequence with a low pressure cell and the isobars. And also when we have a high pressure cell, you also tend to find that the arrangement of the isobars and their values, they also tend to have another sequence which is the opposite of a low pressure cell. If you are having a high pressure cell here, maybe let's say our figure at the center here is 1020. Automatically it means as we move out of the high pressure cell, the pressure tends to decrease. So if our interval is 4, it means the next is going to be 10, 16, and the next is going to be 16 minus 4, that is going to give us 10, 12. And then this one is going to give us 10, 0, 8, like that. So we are seeing the pressure as we move out of the high pressure cell, we are moving away from the center of the cell, is decreasing. And if we move into the center of the high, it will be increasing. So that's the difference that you should note between these two. Like here, we're saying it's subtraction or it's decreasing as we get to the center, but as we move out, we are adding, which is the opposite. As we are getting in, the values are increasing into a high pressure. As we move out, the values will decrease in that direction, moving away from the center of a high pressure cell. Right. Going back to our synoptic map. Right. What do we need to note here? This is a low pressure cell which is existing along the coast. Like if we check, this is the margin of the ocean, which is the Atlantic, and the inland places around Walvis Bay on the western coast. Right. This is what we call a coastal low. It's called a coastal low pressure cell. Coastal in the sense that it occurs along the coast. And these pressure cells, these coastal lows, basically they move from the west and they will disappear on the east end here. They move along the coast in that direction, following the coast like that, until they get to the east and they will dissipate somewhere there in the east. So basically they are low pressure cells that tend to follow the coastal regions from the western coast until they get to the eastern coast when they disappear around Mozambique there. That is a coastal low. So if you get and tend to see a low pressure which is existing on the coast like this one again, this is a coastal low. It's a low pressure which tends to exist along the coast. Then if we check here, we have another low pressure which is over the interior. This low pressure cell here, which exists over the interior, geographically we name it a thermal low over the interior. It's called a thermal low. Thermal in the sense that is caused by heating, which happens over the interior, creating a low pressure cell. And if you also check, we have this symbol here, which is written Elin. This is a symbol for a tropical cyclone. So that symbol, if you see that symbol, it means it's a tropical cyclone. And also, something which is more important, we can see that there's a cold front here, which is existing there. This is typical of a cold front associated with mid-latitude cyclones. Right. So let me just try to extract some of the information here and put it into writing about the position of the cells, the high pressure cells and the low pressure cells, and basically explain on the differences between a summer map and a winter synoptic weather map. Right. I'll just make a sketch and try to illustrate and summarize on the differences on the synoptic maps between a summer map and a winter map, given the differences in temperature and also the differences in the position of our pressure cells. Right, I will make use of our Southern African subcontinent, though maybe the sketch might not be accurate, but for geographical illustration purposes, we'll just use that one. Right, let's assume this is our Southern African subcontinent. Right, and this is on the west, we have the Atlantic, and on the east, we have the Indian. Right. I will start by illustrating our pressure cells, which are typically experienced over the interior. Right. We tend to find that over the interior here, if you are having a dominance of a low pressure cell, like what I've mentioned earlier on, we said it's a thermal low. Thermal low, meaning to say, is caused by heating. When the ground surface is heated intensively, they tend to develop a low pressure cell because of the convection current which set in. So this typical low pressure cell, if you see the dominance of a low pressure over the interior, it suggests that it's summer. The intense heating, which is caused by summer conditions, is the one that will cause the thermal low to develop over the interior. That is typical of the summer conditions. Right. Then also over the interior, for you to determine the season, if you see that over the interior, there is a high pressure cell. There is dominance of a high pressure cell over the interior. Like you can see, there will be an H over the interior here, dominating. This is typical of winter conditions. If you see dominance of the high pressure cell over the interior, it typically suggests that it's winter conditions. And why? This is what we call the Kalahari high pressure cell. The Kalahari high pressure cell is caused by descending air. Descending air, which typically happens during the winter season. The air will be descending from upper atmosphere and exerting pressure on the ground surface, causing a high pressure cell. And this typical of a high pressure cell is called the Kalahari high pressure cell. So if you also check your high pressure cell dominating over the interior, it suggests that it's winter conditions and that high pressure cell is the Kalahari high pressure. Right, that is with the interior. For you to confirm whether it's summer or it's winter, besides checking on the temperatures, you can also confirm with the positions of those cells. And also what you should note, what happens to the Kalahari high pressure cell for it to be replaced with the thermal low when it's now summer. Right, we say the Kalahari high pressure cell is the Kalahari high pressure is vertically displaced. Meaning to say, when it's not dominating over the interior, it has been vertically displaced. Vertically displaced meaning to say, if this is our ground surface, when it's winter, our high pressure cell is over the ground surface here. But now when it's hot, the high pressure cell weakens. It rises. Maybe it's now there. It's now very weak. It's not dominating the ground, but it's now in the upper atmosphere. That is vertical displacement. Because of the intense heating, the very high pressure cell is vertically displaced. That is how it changes its position. When it's summer, it's somewhere in the upper atmosphere, it's vertically displaced. When it gets to winter, it becomes stronger. The strong descending air is going to force the high pressure cell to dominate over the surface. That is how it changes its position. Right. So we move on to our two pressure cells, our two anticyclones. We have one, the South Atlantic on the west, high pressure. This one here, the high pressure which exists on the western part, on the western coast is the South Atlantic high pressure, and this is called the South Indian high pressure on the east. We have the South Atlantic on the west, and we have the South Indian on the east. So this is the South Indian high pressure. Right. So what happens to these two high pressure cells for us to figure out if it's winter or if it's summer? Right. I think we understand the concept of, let's assume, of the ITCZ, the Intertropical Convergence Zone. Right. When this ITCZ, it shifts with shifts in seasons. When it's summer in the southern hemisphere, our ITCZ will shift further to the south. It will move. The overhead position of the sun is somewhere to the south of the equator, somewhere around the 23.5 degrees line, which is to the south, which is the Tropic of Capricorn, which means it's summer conditions in the south. These high pressure cells, they also tend to move latitudinally with the shift of the ITCZ. When it's summer, they are further to the south. They are not adjacent to the African subcontinent. They are somewhere south here. So if you see the South Indian somewhere here, it's not latitudinally positioned around the South African subcontinent here. It's somewhere further to the south like this. If it's here, it suggests that it's summer conditions. It's summer. In the southern hemisphere, it's summer. But when it's now winter, remember the ITCZ tends to shift north of the equator until it gets to 23.5 degrees north, which is the Tropic of Cancer. Right. So given that situation, the ITCZ has shifted further to the north because now it's winter in the southern hemisphere and it's summer in the northern hemisphere. Our two high pressure cells or our two anticyclones, they also tend to move latitudinally. They now move to the north. If they are placed here, you see your South Atlantic, you see your South Indian here. It is a suggestion that its winter conditions in the southern hemisphere, they are now adjacent to land here. So the shift of them is an indication that there is also a shift in the position of the ITCZ. The further the north the ITCZ goes, the further the north, these ones also move. They move until they get adjacent to the southern African subcontinent. And when the ITCZ shifts further to the south, when it's now summer in the southern hemisphere, they are also further to the south, further away from the latitudinal position of our southern African subcontinent. So that is an indication. You see them here, know that it's winter in the southern hemisphere. You see them further to the south, it suggests that it's summer for the southern hemisphere. The same happens with this South Atlantic and the same with the South Indian high pressure cell. Right, that is the position of those cells and how they show you whether it's a summer map or a winter map. And also the other things that also indicate, besides the position of those cells, you can also take note of other weather phenomenon like the mid-latitude cyclones. They are also a very clear indication of whether it's typical summer conditions or it's typical winter conditions. Right, our mid-latitude cyclones, they are indicated by the cold front and the warm front. And you should check their position. We said mid-latitude cyclones, they occur throughout the year. But however, they affect South Africa or Southern African region in winter, which means if you see mid-latitude cyclones appearing on the synoptic map on the western part of South Africa, it suggests that it's typical of winter conditions because that is when they affect the southern western coast of South Africa. Assuming this is our map, right? You see maybe here, there's something like this. And then something like that. And then maybe it's occluded. There's this. It's happening to be on the western coast and it's approaching land. Maybe it's a family. There's another one, maybe somewhere there. These symbols. These are weather systems. They move from the west going to the east. And if you see them getting into the interior here, this is a suggestion that it's winter, because they affect the western coast of South Africa during the winter season. If you see them getting into in the interior, it suggests that it's winter conditions. And sometimes you tend to find that you see them, but there is no potential of them affecting the western coast of South Africa, because we said they occur throughout the year, but we are only worried about their effect into the southern African subcontinent, the western part. If you see them here, maybe you are checking on another synoptic map, you see maybe there is the cold front and warm front somewhere there, which is further to the south. Our southern African subcontinent is ending there, and this weather system is moving from west going to east. Is this going to affect southern African subcontinent? No, it is going to move over the ocean and disappear there, which means this is typical of summer conditions here. These systems are existing, but they are not affecting us. They are somewhere further to the south, and they will just occur over the water body and dissipate on the water body without affecting the west. Right, that is typical of other indications of the summer and winter conditions. And also, besides, you are also supposed to check on the date, which is a clear indication. Check the date of the synoptic map. When was the map actually compiled? And there you need to give a justification. When you check on the date, you see it's June. Maybe it's June 16. Right, that's the date. Give a justification. Why are you saying the date is suggesting that it's this season? June 16, we know that it's winter in the southern hemisphere. June is a winter month in the southern hemisphere. So that's a justification of the season. And also, if you check, maybe it's saying January. The map is saying January, maybe 25, 2024. It means that one is a summer map. Why are you saying so? Because January is a summer month in the southern hemisphere. There's no way we can have January in winter. January is typical of a summer month in the southern hemisphere. So if you see that the map is having a date for January, then it's a summer map. And if it's having a date for June or July, that is typical of a winter map. Then that is basically what you need to check on the synoptic map to find out if it's a winter or a summer map. You use some of those indications to determine whether the map is for winter or whether the map is for summer. Right, going back to our map, I think that is basically what is indicated there on our maps. Right, so we want to quickly look at the questions here, which are based on the synoptic map indicated here for Cape Town. Right. The Cape extract is coming from Cape Town here, as it has been enlarged here so that it becomes clear for us to be able to figure out what is being shown on that synoptic map. So the enlarged weather station is indicated here with 2911 and that shaded circle and this bar and there, that one there. What is the question saying? Determine air temperature. We said air temperature is the maximum temperature. So we are taking between the two. There's 29, you can see there, and there's 11. So when we're talking of air temperature, we said that is the maximum. Between the two, 29 and 11, it means 29 degrees Celsius. That's the air temperature. And then the dew point temperature automatically becomes the lower, the smaller number, which is 11 degrees Celsius. Then if we check on cloud cover, we said our cloud cover, we find it in the circle here. The shaded part of the circle is indicating the cloud cover. So our cloud cover, if you are to indicate there, that is 4/8. And the present weather, what kind of weather is that one? We have a temperature, maximum temperature of 29, minimum temperature of 11, cloud cover of half. What is kind of weather do we have there? Basically, the weather is fine. Yes. And it's a fine weather, it's a warm weather. Then wind direction, we said this bar here indicates our wind direction. So our north is there, our west is there. North, west, south, east. So our wind direction basically for that one there, wind direction is north, west or north, northwest. That is basically our wind direction. Then the air pressure is indicated there when we want to figure out the air pressure for that particular. We use our ISO bars. If we come here, we want to check the air pressure around this ISO bar here. Right. We are seeing that the next ISO bar to this one here is our 1024, and this D is not indicated. We are supposed to find it. And then there is a 1016. So if we try to figure out our interval, the interval is 4. We are moving from a low pressure cell here. 1000, 1004, 1008, 1012, 1016. Definitely for us to find D here, it's 16 plus 4, which gives us 1020 and 1024 and 28. So if we try to check the next pressure isobar, which is close to Cape Town, we can figure out that the pressure is between 1020 and 1024 because this isobar is stretching and is getting closer to Cape Town, whilst this one is also coming on this side. So basically the air pressure, the most closer isobar is 1024 to Cape Town. So that is the justification of our pressure there, around 1024. Then we go on to wind speed. Our wind speed is indicated at the end of the feathers of our bar here. Our bar is ending there, and we have this one feather here, which is full, which means for one full feather is 10 knots. Right, that is basically how we can answer those questions based on the given synoptic map. Name the lines that are used to join places of equal air pressure. We have talked about that. That is an isobar, according to our previous discussion. Then the season that this chart represents is, right, is it summer or winter? Let's look at the justification of whether it's a winter map or it's a summer map. Indication number one, there is a high pressure dominating over the interior there. What does that imply? It implies that there is sinking air and the Kalahari high pressure cell is dominating over the interior. That is one evidence. And also, let's check the position of our South Atlantic and South Indian. If we check, our South Indian is somewhere there adjacent to our Southern African subcontinent. Our South Atlantic is also somewhere there almost adjacent, which means they've moved further to the north, which is also typical of winter conditions. So given those two, we can safely conclude that it's winter. And also, if you come to our date, this is 2000, June 6th. June, like what we have been mentioning, is typical of a winter map in the southern hemisphere. And also, if we check our temperatures, maximum is 29 and minimum is 11, which also suggests that the temperatures are not very high if you're having a maximum of 29, which is typical of winter conditions. Right. So we have a lot of evidence which gives us the justification that this map is a winter map. Identify the pressure cell labeled A. Where is A? This one we've talked about that. Labeled A is on the east. This is the South Indian high pressure. And also, compare the spacing of these lines to 422 B at B and D. Where is the wind blowing at a greater speed? Right, when you're talking of winds blowing at a greater speed, the closer the isobars, the strong the wind. And the further apart the isobars, the weaker the wind. If isobars are closely located like this, it means if this is high and this is low, our isobars, there's going to be a steep gradient here, and the winds are going to be strong. But if our high pressure is there and our low pressure is there, our isobars are like this. There is a general gradient which will give us weak winds. There will be light variable winds in that direction, and here there will be strong winds. So the closer the isobars, the steeper the gradient and the stronger the winds. But if they are further spaced apart, it will suggest that there is weaker winds. Right, pressure cell at E is a coastal low or heat low. Right, let's go to E and check where is our E. Our E is here. Right, a low pressure at E. We talked about this. This is the coastal region along that line, and that cell is existing along the coast. So automatically it's a coastal low. Pressure reading at D, we have talked about that. That is 1020. We have calculated it already. HPA. And then the pressure increases or decreases to the center of F. Let's look at where F is. Right, let me erase some of the markings on the map to make it a little bit clear. Right, let's check where our F is and determine whether the pressure increases or decreases towards the center of F. Right, based on this, we are checking on our map to see where F is located so that we are able to figure out. Right, if we check on our map, our F is located here. This is where our F is. Our F is here. And the question is saying the pressure increases or decreases to the center at F. Let's look at the sequence here. Is F a high or a low pressure cell? Is 1016, 1012, 8, 4, 996. Our pressure is decreasing towards the center, which means that is a low pressure cell. Our pressure values are increasing as we go towards the center of F. So it's a decrease. Right, then the last one, another name for a high pressure at G is a cyclone or anticyclone. Whenever we have a high pressure, like what I've been mentioning, We have the South Atlantic high pressure, the South Indian high pressure, the Kalahari high pressure. All those high pressure cells, they are summarized as anticyclones. So all high pressure cells, they are anticyclones. And low pressure cells, they are cyclones. So basically, a cyclonic weather system is a low pressure system. An anticyclonic is a high pressure system. Always remember these two: high pressure, anticyclone, low pressure, cyclone. That is basically what we're supposed to focus on when you're looking at synoptic weather maps. This basically has taken us to the end of our discussion, and it is to my belief that the discussion is going to help you all along in your studies for geography, in preparation for your tests, in preparation for your SBAs, in preparation for your examinations at the end of the term, at the end of the year, or whichever course you are taking. So basically, I think we have touched on the key aspects of synoptic weather maps. We've also tried to elaborate on some key aspects and key concepts which are of paramount importance towards your understanding of the reading and the interpretation of synoptic weather maps. Till we meet in other discussions, your host, Conrad Mupinguri. Thank you.